other than assignment 2. I should have put that caveat.
Sounds like.
Yes,
One will assignment, one grades the other.
I should have them all graded by next Wednesday. Yes,
What's going to be on exam
on exam 2,
Yeah.
Oh,
2 chapters. I'll put the study guide up the Friday. Other questions? Yep, chapter 3, chapter 4, exam 2. Other questions?
oh.
So you've, yes.
We're continuing where we left off last time, right?
Yeah.
I don't know, I felt like I was a little iffy on segmentation.
Well, let's review it. That's the kind of question I was hoping to hear tonight, because I was just getting ready to ask everybody. So this means everybody's absorbed everything that we turned the fire hose on Wednesday night, right?
No.
Let's go over segmentation again. I would really like that.
So, let me pull that. Okay, so what specific question do you have?
How does it relate to paging? Are they two methods to do the same thing? Is one part of another?
For segmentation,
And
paging,
paging.
or segment paging?
So by itself, is it a replacement? Are they designed to do the same thing? Or is one supposed to help with the other one? Or where does segmentation fit in?
So the
the scheme
segmentation
of
is
memory
a,
management.
yeah, segmentation is an alternative to paging.
Okay, so there we go.
Except for the case where we adopted page segmented memory systems. That one we talked about where we're using both of them combined. So if we talk about just segmented memory and segment address mechanisms, then we're talking about just this by
Okay.
itself. If we're talking about paging, then we're looking at strictly by itself the paging technique. If I want the combined paging and segmentation, I will so state, in which case we will use the combined segmented paging system that we talked about.
Alright, so in that case, you have segments which are comprised of pages, which stores the data.
Right, we're gonna form the segments, right? And we're gonna fit those at compile time, not runtime, into pages. So that part of the work, searching and reducing external fragmentation, is taken care of at compile time, not at runtime.
Okay.
That's the big difference between those two by themselves and this combined technique. Because at runtime, remember we talked about, it's gonna be very, very costly to manage our free list. Because they're all different sizes. And we start developing these holes of different sizes, which over time are growing and shrinking, stuff like that, causing lots of external fragmentation, which is bad. Plus, trying to find a large enough free space without having a whole lot of, without having a lot of management tools is really hard. So, instead of trying to do that at runtime, just do it at compile time, put it into pages, and that gets us the best of both worlds.
Clear.
Other questions? Yes?
I'm a little confused as to what the base and the limit registers purposes.
Say again?
I'm a little confused as to what the base and the limit registers purposes are.
So base registers tell you the starting address of that particular frame.
Is it like an offset?
Base? No.
No,
It's the
but
start.
what about the limit?
The limit is going to be the maximum size that you can generate. That's part of our memory protection scheme, right? Because I do not want to allow a process to be able to access an address outside of its memory space.
Okay.
So that's what that provides us, is that
Just
protection.
give us a chunk of memory?
So yeah, we'll fix it. So if it's a paging system, it's gonna be fixed to the size of a page. If it's a segmented system, then it's gonna be the size of that segment. Other questions? If you have the questions, somebody else in here does too. Yes?
Can you go over the, or like the walkthrough or like the flow of the combined segmentation and paging algorithm?
Sure.
Just like briefly, maybe just this diagram.
Let me, before I start talking, I'm gonna ask if somebody else thinks that they understand it. Of course, you're sitting there silent because you're saying, you're filling in the blank, right? Think I understand it enough to describe it to all 60 of you? Sure. Does anybody think they do? I tell you what, you'll never forget it if you do.
I think I
Okay.
partially got it.
Partially got it? You wanna give us stuff?
I mean, you start with the segment number, and you probably add that to the segment table pointer to get the address of the page table for that segment, and then you use the page number as an index or an offset into that table to get the frame number,
And the starting address for this page table.
right, for that
is-
page table, and use the offset added to that to get the actual page entry, which is an address, a physical address to the frame, and you add the offset to that one to get the physical address of, in memory of that element.
You nailed it. Anybody not follow that? Excellent, well done. Good. Okay. Other questions? No? Thinking about it? Oh, okay. I'll have questions. Not tonight. Okay. Then, that's annoying. Okay, so picking up then from where we had left off, we talked about, obviously, the addressing schemes for these different techniques of managing our memory space. And we've talked about the fact that we're going to have more pages than we are going to have frames. And we talked about frames are coming, they're going to get loaded in, they're going to swapped out, and all that kind of stuff. And so we've been kind of avoiding this whole question about how do I select some poor page to remove from main memory and swap it out. Of course, we also remember about the dirty bit, right? Okay, that's all part of that architecture we talked about. As well as in memory and all those control bits. Don't forget those. But now what we're concerned about is actually deciding which page to kick out of a frame when I need a frame. And it's kind of a big deal, because I'm sure a bunch of you ran home after Monday's lecture or yesterday and looked at the statistics, the number of page faults your system's generated, right? Because you forgot to do it over the weekend and you were gonna run home and do it, remember that? So it happens a lot, very, very frequently. That means we need an efficient algorithm that's going to optimize the system performance, because it happens so frequently that any little improvement we can make is going to make a huge improvement over the runtime of this operating system, which makes it better for our end users, well, and ourselves, because we're also end users on our systems, right? So that's what we want. Okay, so that's what this fetch policy is all about. It's all about determining which page is the best one to choose to swap out when I need that frame for some other page. Okay? There's a couple things to think about we can do that's sort of above and beyond which algorithm we select. One of the things that you can do is you can do a technique where you're going to select all of the memory resident pages, automatically load them up for a process, and then only fetch those pages as needed. That's one technique. Okay, so when I say fetch one page, of course, if all of our frames are in use, then I have to select a page to remove from that frame so I can insert this frame that I now need into that frame location. Okay, so that's one technique. That's called demand paging. Okay, that demand paging technique was effective when it first came out because it recognized that we could be more efficient about how we're using our space. However, it takes time to move memory, move contents of swap space into a frame, right? Because we're going out, we're doing a disk read, moving it into the system, this whole block, into this determined location and frame memory, and we're having to wait for that to complete while our process is running, which means it's having to go to sleep and then come back in, right? So there's some inefficiencies there. So then we came up with the technique of pre-paging. Now, of course, this comes back to tools like the TLB and the TLB cache, right? Having the TLB and the TLB cache allows us to be able to do things like pre-paging, where we can predict the future and say, if I'm going to request this page, I'm probably also going to request this page, and this page. And so instead of fetching one page, maybe you prefetch 4 pages. Okay? And that's been proven to be very efficient for those systems that have TLBs and cache buffers, to be able to bring in more than one page when I say, I need a page. It's not in a frame, I need a page. And our compiler can actually pre-code this, predetermine this, and say, you are most likely to use these other additional pages shortly after this page. And so that information is passed to the loader. The loader then adds that to some administrative routine that we're not going to talk about in this class. That allows us to then determine which pages to also prefetch whenever I select that one page.
So these are all simply directives that are controlling all this essentially?
Yep.
So like your architecture, if you're writing like x86 architecture, you can do all this yourself.
Yeah, you could, well, not in x86. Well, yes, you could in x86.
Well,
Advanced
x86 is
x86.
yeah.
Yeah.
That's wild.
Yeah, isn't it? Right there at your fingertips. And the savings, the improvement in speed is huge. But you have to have the hardware. Right? That's the key thing. Speaking of having the hardware. Not everybody. Okay, so now we come to the replacement policy itself. Okay? All about which page are we going to replace, which frame am I going to free up. Ideally, when I need to bring a new page into memory, I want to select the frame that I'm going to reference the furthest in the future. Okay? So if I have 20 frames, if I had 10 frames, and I had some omniscient way of knowing that the page that's in frame 3 will be the last one of those 10 that I reference. I'm going to reference all of those others before I select 3. It's going to be the very last one. If I wanted to select one page to pull out of main memory, that would be the one. Okay? The problem with that is hopefully obvious. We have no way of knowing. Right? At runtime, we have no way of knowing which one of those is going to be the furthest out in the future. There's lots of conditionality that's going to prohibit us from knowing that. But if we could be omniscient, that would be the very best. Why do I stress that? Because it's going to be important to us to understand that as we try to analyze these different algorithms and have a benchmark to compare them against. Why not benchmark them against the very best? More about this later. But that's what we would ideally like to do. But instead, what we try to do is to best predict the future. And we're going to take a look at several different ways to do that. Okay? All of these techniques that we're going to look at is going to have to adhere to this thing called frame locking. We're not going to talk about it in the course or in our discourse of these different algorithms, but bear in mind that frame locking will always usurp any decision we make. The idea with frame locking is that I may have some frames that I cannot select, i.e. the ones that are memory resident for the running process. A few very important kernel-based processes, memory resident frames, things like that. We have to have the ability to make sure that certain pages are always memory resident. The way we do that is with frame locking. So if the CPU, while it's in the kernel executive mode, determines that that frame needs to be memory resident, it will so lock that frame, and it will then be not part of this whole evaluation process and assessment and selection process that we're going to talk about the rest of the night. Got it? I'm not going to say it again, but that's true. Okay? So, what we're going to talk about tonight are these 4 algorithms. There are others. Okay? And your authors listed some of the most popular, and there's even others beyond those, of course, but you're going to be responsible for the ones the authors wrote about. I want to focus on these because if you understand these, you will easily understand the rest of them that are in the textbook. Okay? The first one is our optimal algorithm. Again, we want the optimal algorithm because, I know we're not going to be able to implement it, but if I can create the optimal choices for frames to remove, to be replaced with the frame that's being requested, the page that's being requested, if I can choose the best path, the best selection, then as I go through and assess each of these other algorithms, I can compare them against the best in this simulation environment. I can compare them against the best instead of each other. Because, and we'll talk about this a little bit later, because these different algorithms are going to behave differently based upon number of frame sizes, the actual sequencing that you're accessing your pages, and a couple of other issues that we'll talk about again a little bit later, could cause them to behave differently, where in some cases one algorithm will be better than another, but not in all cases. Change different frame sizes, I might get different performance. But if I have optimal, it will always be the best. So I'm going to always compare against this best. And I'm always doing this analysis in a simulated environment so I can compare it against an optimal algorithm results. Okay, so we're going to take a look at optimal. We're going to take a look at first in, first out, least recently used, and a very popular algorithm called clock. Again, you're responsible for all the ones in the text. We're going to study these, talk about these rather in class. Okay, so again, optimal. The one that's going to be referenced the furthest in the future, that's the one that gets kicked out. Don't know it during runtime, we're going to use it for our analysis. Diagram that just to make sure we understand it, because you like to just sit there and say yes, 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 yes. Yes, yes, yes. We'll make this even simpler. 1, 2, 3, 4, 5, 6. Numbers 1, 2, 3, 4, 5, 6. So, my process starts up and it wants to run page 1, then it wants to run page 5, then it wants to run page 6, then page 4, then page 2, then page 3. Okay? So so the first 6 pages it may access, maybe some order like this, 1, 5, 6, 4, 2, 3. Okay? That's fine, that got these all in main memory. So now the question is, it wants to access page 7. And based upon just that, you're supposed to make a decision. Which one of these do I want to kick out? And this is where all these algorithms come into play, because if you're looking strictly historically, you don't know. Well, in runtime, that's all we have, is what's happened historically. So we're going to look at some algorithms that can get us to best approach optimal, which I moved ahead of. So we want to study these algorithms and compare them against optimal because it's going to know the future. It may know, for example, that I'm going to next access 6, 1, 2, 5, 4, 3. Okay? So if I say, 6 is the next one, I want to keep that in main memory. 1 is shortly after that, I want to keep that in main memory. 2 is getting further away, but it's still close, I want to keep that one. 5, okay, I want to keep that one. 4, well, that leaves 3. That's the one I want to kick out and put 7 into. Right? That's the one I want to kick out and put 7 into.
So your table, your array should only have 6.
I'm just using this as a notional diagram to help us understand this concept. Reality is I have a bunch of frames. These were by pages. They can be loaded at whatever frames, but they're the only frames I can consider for this particular example. Okay. So that's the idea behind optimal. I want to go to the one I'm going to access the furthest out to the future. Now what's kind of another, elaborate here. Another artifact of this very poor example here is that it's assuming that I'm always making a different page request each time. I could do this. I could go 6, 1, 6, 1, 1, then 2, 6, 1, 1, 5, 4, then 3. At that point, that's when I've used the previous 5. That would be the one furthest in the future I would select. So I would have something more like this than I would be, I'm accessing each one at a time. Okay, so runtime, matter of fact, that's one of the challenges that we have at runtime is a lot of times we're going to sit there on 2 or 3 pages most of the time. We'll be sitting on 1 page a lot of the time. And then we might be doing some other 2 or 3 pages. And then you start making some odd requests. And then you come back to your memory residence set again, and you can do that, right? So this is closer to reality, although even that is, it's just an example to work from. The idea behind it, though, is what's important to understand because that's why these algorithms are so important. If I can predict the one the furthest in the future, that's my optimal or best decision I can make. And that's what we're trying to get at, so we can look at the results here and get our other algorithms tuned to approach this number. Okay? Also, as a reminder, I believe we talked about this before, but as a reminder, these page fault algorithms are so called because a page fault was generated, which meant that the process needed to access a page that was not loaded into a frame in memory. Correct? That's just review, right? Thought so. All right, so that's optimal. How do you implement that? There's different ways to approximate it. There's different ways. In a simulated environment, it's not too hard to do, because in a simulated environment, you actually get to look ahead in the future and then run your algorithm that way. Okay? That's the whole idea of doing this in a simulation environment. Okay, so let's look at the first so-called real one. Okay, first in, first out. The way first in, first out works is it treats each of the frames as if they're in a circular buffer. Right? So you put a page into the first frame, you put a page into the next frame, put a page in one after that, and then when you get to the end, it's like a circular buffer because you're just going to remove the oldest one and put the new one there, right? I'm just using my fingers when I have a whiteboard. How about that? Now it's about the dining philosophers. So we have 6 comes in. 6, 1, 2, 3. There we go. 6 comes in. 1 comes in. 2 comes in. 4 comes in. 3 comes in. 5 comes in. The next one that comes in goes here. So I'm keeping a pointer, right? Always keeping this pointer here, pointing, I just put 7 there, to the next node that's in this FIFO system, right? And that's all I'm going to do is first one in, first one out. Pretty simple to implement.
So
Yes.
you make a pointer to the oldest page.
Right. Yes, it'll always be to the oldest. That's why we put the first into the oldest. Next first, I should say. Right? So that's pretty simple. Problem with this is that when I started getting to these scenarios here where I might have some nearby references and I might kick out 1, I do 2, and then I want 1 again, right? And so I might just kick out a frame that I'm going to use again that has absolutely no retention or knowledge of any frame that had been used and should maybe stay in the system longer than pages that haven't been used in a long time. Okay, so we're just going to simply kick out the oldest one. So that's a problem because we have, as you will see, perhaps in your studies, that that's very inefficient because a lot of times we are interested in frames that are used frequently, are used more recently than others, not necessarily the oldest one that was ever inserted into our frames. Big difference between recently used and how long ago it was put into a frame. Okay? So first in, first out, very simple, which means it can run pretty quickly. However, will probably generate a lot of page faults, a lot of unnecessary page faults, because we're not taking into context or into our decision logic how frequently pages are used or how recently pages are used. Okay? Yes?
What's the second chance variation?
Let's talk about these first and we'll come ask some questions about those.
Variation.
I know it's a variation, it's on your assignment, you read the assignment, I got it. I understand the basic algorithms here first. Okay? Other questions other than that? On the basic first in, first out. No? Okay. Good. Let's take a look at least recently used then. Okay? Least recently used is very popular because it's the basic LRU is kind of crude and clumsy, but it can be implemented very efficiently and you get a lot of performance improvement with LRU. Okay, so the idea with LRU is that we want to take the page that hasn't been referenced in the longest time and get rid of that one. Not the one that was put in the longest ago, but the one that I accessed the longest ago. Okay? Because in this scheme here, I was only kicking one out, putting one in, if I accessed a single page that was not in a frame, like one. I selected, if I had, who did I kick out? 1, 2, 3, 4, 5, 6. So if I access 6 again, which was in here, and I just kicked it out, then I have to kick one out, put it here, but then I'm gonna access one again, I'm gonna have to go around and do the same thing. So it's pretty inefficient from that perspective. Whereas the idea with least recently used, if I had just recently used one, I would then say, no, I wanna keep that one. Let's skip over that one and choose somebody else. Okay? This has been demonstrated through many research projects to be much more efficient because of the locality of reference principle. Right? Where you are in your code, a lot of times you are spending a lot of work inside of several functions that are fairly close to each other in memory. And so therefore, they're going to be, even if they're not memory resident, therefore they're going to be in memory more frequently. They're going to be frequently accessing those same functions. You probably want to keep those inside of main memory and get rid of that esoteric one that's only used occasionally, right? Because you do that. You build functions which are the mainstay of your programs. For these larger programs, there's a number of functions that are used over and over and over again. They're the base set of functions, if you will, or objects or methods. And those, you want an algorithm that keeps those in main memory most likely. And that way, every once in a while, the user might say, okay, let's go ahead and print something, because I hate printing. The printer never works, right? So you always want files. I got files, I can read files, I don't have to carry paper with me and all that weight and stuff, and the printer never works. Did I say it before? So if you have functions like that, you say, oh, okay, let that one get swapped out. I don't use it too much. It's only at the very end of all my calculations anyway that this user is going to print something. So, yeah, so those are reasons why FIFO aren't very good. And it's sort of a description about how locality of reference works from a general sense anyway, to kind of make us think that, hey, there really is something to this LRU concept. Okay, so to implement this, we're going to need a way to tag each of our pages each time they are referenced. Okay, we need some sort of tagging system so that we can age each of our pages, or in this case, what we can do is we can freshen the age of each of our pages every time it is referenced. So the one with the biggest number stays in the longest, right? And you kick out the one with the smallest number. That would be the idea. Okay? Any questions about the basic concept of LRU? So implementation, pretty straightforward, although a lot of time could be spent on this part here, where this whole, how do I age this, or how do I freshen the age of this thing? And that is where most of the work on LRU takes place in its variants. Okay, so there's some good reading in there on several variants to LRU. And we spend a lot of time on that because, as I mentioned earlier, LRU in its basic sense is really easy to implement. To gain some efficiencies, a little bit of tweaking, you can get something that works rather well for low cost. Low cost being amount of complexity of the code, which is good. Questions, LRU? Okay, then there's clock. Probably one of the more complex ones to talk about. There are more complex algorithms out there, but, oh, they didn't erase that one. But none are practical. The thing about the clock algorithm is it's very practical to implement, even though it's a little bit more complex than others. And so it's often looked at as a possibility, although a lot of the LRU variants are preferred over clocks. So it all depends on whoever's running your team.